I'll say hi, but I probably will turn it off for the duration of the session. Just I find it distracting to see my own face talking back at me. I'm sure everybody gets it after the past year. So hi everyone, welcome. My name is Anne, as the screen says. I work at Efficiency Nova Scotia. I manage the commercial and new construction program here. So within that program, I do lots of work with energy models and with the NECB. So I'm going to be chatting with everyone today about the NECB. So yeah, thanks for coming, and hopefully this will be a nice, no distraction for folks from all of the talk about the pandemic and the restrictions and everything that's happened this week or so. So we can just kind of dive our brains into the energy code instead. And I just wanted to, I guess, just do a little check-in about like why we're here and what we're going to be talking about. So if you do want to know what is the NECB and how do I use it, then awesome, you're in the right place. If you want to know how to design or construct an efficient building, I won't really be covering that today. That's a whole different kind of topic. For that, you can definitely contact Efficiency Nova Scotia. You can email me or anybody else, but also still stay tuned because you might learn something about the NECB. A quick agenda, intro to the code, history, development, application, adoption. I will give an overview of prescriptive requirements and performance path requirements, though for both of these, I'll be focusing on envelope and HVAC, as these are systems that pertain to, space heating within a building. So if you're here for lighting, I'm sorry, that won't be part of the talk. Okay, so jumping right in, NECB development. So the NECB is what's called a national model code, so developed at the national level, like the National Building Code, the Plumbing Code, the Fire Code. It's developed by the Canadian Commission on Building and Fire Codes, along with NRCan. The first edition of the NECB was the MNECB, M for model, 1997. And then since then, we've had 2011, 2015, 2017, which is the current edition, and then 2020 in progress, slated to be released later this year. The code, like what it's actually for, the objective is to establish minimum energy efficiency performance targets. And the targets become requirements when they're adopted into law by the authority having jurisdiction, which is provinces or municipalities. The code, like the scope of the code, is not inclusive of all energy uses in a building. So it's primarily looking at HVAC, lighting, surface water heating, a couple other things. But there are lots of energy uses in a building that aren't necessarily covered by the NECB. As far as where the code applies, so buildings obviously, but new buildings that comply with Part 3 of the National Building Code. So what this means is buildings that are large enough that they don't qualify for housing or small buildings. It also applies to additions to existing buildings. So if you have an existing Part 3 building and there's going to be an addition, the NECB would apply. The NECB does not apply to houses or low-rise multi-unit residential buildings. These are covered in the National Building Code Part 9, and within Part 9, there's a section 9.36 for energy efficiency requirements in those type of buildings. The NECB does also not apply to renovations of existing commercial buildings. So if we have a large building that is undergoing a retrofit, even if it's a deep energy retrofit, that building is not subject to the requirements of the NECB. There has been some talk about developing a specific retrofit code, but that would likely not fall into the NECB. It would be its own code. In Nova Scotia, like I said, we're currently using NECB 2017 as of January 2020, but before that we did have the other codes in effect. So really we've been using this code for quite some time in the province, and we've just been slowly changing or adopting new codes as they become available, which is really good, right? And like I said, that it has to be adopted into law. And so in Nova Scotia, it's in the Nova Scotia Building Code Act. And that's also where the province can make minor amendments to the NECB, change, the small things about the code to make it applicable for what we need in the province. Compliance and permitting is governed by municipal permit offices. So each municipality is responsible for compliance with the code. Future versions. So I mentioned that NECB 2020 is slated to be released later this year. Last I heard, I think it was going to be for December. The NECB 2020, and I just briefly wanted to go over this because it is an important change to the way the code will work. It's called a tiered energy code, and what that means is there are different levels within the code. Looks something like this. So tier 1 would be just the standard, whatever NECB 2020 says, and then tiers 2 to 4 are just percentage increases above that NECB 2020 standard. 25, 50%, 60%. What that means, or the reason that this is kind of useful, is if the province, say, adopted the NECB at tier 1, so they're just going to go with the 2020 requirements, and then a couple years down the road, they wanted buildings to be more efficient, well, then they could jump up to tier 2 and then tier 3, etc. It makes it a lot easier for industry because everybody doesn't have to like learn a new code every time, right? We're still using the same code. We would just be, improving the efficiency within the same code. So I think that will really help when that comes out. So looking forward to seeing that. Potentially a revision in 2025 available, and then 2030 is slated to be the net zero ready version of the NECB, which will also be really interesting to see how that looks. Also briefly wanted to cover the adoption across Canada because even though this is a national code, it's not consistently adopted across provinces. So this table here is showing the different energy codes in different provinces. And so you'll see Alberta and Saskatchewan are along with Nova Scotia with having 2017 effective, but other provinces some of them are using 2015, and then BC and Ontario each have their own energy codes that they've kind of developed themselves that are slightly based on NECB, but also some ASHRAE content and also some of their own content. So there's not necessarily consistent practice across provinces. And even with that, when a province adopts the energy code, that doesn't necessarily mean that the province is enforcing the energy code. So not only are there different codes, there's different ways that the code is enforced in different provinces. And enforcement, is its own process. There's a lot of work that goes into that. And so it is difficult to make sure that every building is complying with every part of the code. And the more strict the code gets, the harder it is to enforce it, right? So yeah, just something to keep in mind. Okay, so jumping into NECB and how it actually works. So if you're familiar with the NECB, you will know already that there are prescriptive and performance paths. The prescriptive path is, as it's called, prescriptive. So there is specific criteria that have to be met for each building system. So for example, all walls would have to meet the maximum Uvalue criteria. And within, or I guess similar to this path, or related to that path, there's a trade-off path. So say if you have, one wall that doesn't meet, but one wall that does, or that's over the requirements, then you can kind of use a trade-off, which is, it's just slightly more flexible than the prescriptive path, but it's still a rather kind of, prescriptive or defined option. The performance path is the way to comply with NECB using an energy model. So in the performance path, the total model energy of the proposed building must be less than the reference building. And the reference building is defined by the NECB, and it's generally represents the prescriptive path version of the proposed building. And so where we might use these different pathways, the prescriptive is certainly useful for like small or simple projects. There is less flexibility, like I said, but the benefit is that modeling is not required. So you don't have to go through the process to actually generate an energy model to comply with the prescriptive path. The performance path is great for larger or complex projects. It allows for a lot more flexibility in the design. So this path is great for buildings that say have a lot of windows. Like if you see like a tall glass building, it's probably going performance path. And like I said, the compliance in that path is based on modeled energy use. So the building must be modeled. And so prescriptive requirements, like I said, I'm focusing mostly on envelope and HVAC here, sticking largely to envelope because the prescriptive HVAC is fairly straightforward. Before we look at prescriptive requirements, we do have to understand which climate zone we're in. And so folks already using the NECB will probably be familiar with this, but there are different requirements for each climate zone in the country. And the zones are based on heating degree days. And if you're not familiar with heating degree days, in general, a higher number means colder. So here are the different zones within Canada. So Zone 4 is the warmest, Zone 8 is the coldest, and most of Nova Scotia is in Zone 6 for buildings that are heated above 15 degrees Celsius, which is generally our occupied buildings. The exception to that is that, interestingly, Liverpool and Yarmouth are both in Zone 5 because they have less than 4,000 heating degree days. And if we have a semi-heated building, so anything that's heated below 15 degrees, which is maybe like a warehouse or an ice rink, those would be in Zone 5. Okay, so with those climate zones, keep that in mind. Oops, sorry, clicked the wrong button. All of the requirements that we're going to talk about are the requirements for Zone 6. So the requirements for the envelope in Zone 6 look like this, and I've included the requirements from NECB 2015 and 2017, so we can take a look at the changes. The only change in the opaque envelope was in roofs, and so we went from an R value of 31 to 36 in the newer code. The NECB always reports things in U values in SI units. That's why I've got USI here. But I find, personally, I find a lot easier to think in R value space, and I think a lot of people would agree. So the R values are here. But yeah, so we've got walls above grade are at R23, below grade it's R20, floors are 7.5, though for the floors, when they say R7.5 in our zone, that's are 7.5 for just 1.2 meters from the wall under the floor. Okay, it doesn't have to be the entire floor. And when we're looking at walls, both above grade and below grade, but certainly important for the above grade ones, this minimum R value of R23, this is the effective R value. And I'm going to talk about this a little bit because this is pretty important. So if we go out and say like buy some fiberglass bat and it's R24, that doesn't necessarily mean that we're complying with the code, right? So we need to understand the actual effective R value or effective U value for the wall to make sure that that value is compliant. And that's what the NECB calls the overall thermal transmittance, which I call effective U value, which is the representative U value for an assembly accounting for the varying heat transfer paths, which is commonly referred to as thermal bridging. So when we account for thermal bridging, what's the effective U value, and does that value meet the NECB requirements? And like I say, I think this is fairly important, so I'm going to kind of go over how this works and also how this looks in NECB 2015 versus NECB 2017. So in the 2015 code, we did have the requirement that the envelope assembly U values have to account for the thermal bridging of studs and joists, or as the NECB says, it's the, what do they call it? Repetitive structural members. So the studs. And it only needed to account for any intersections, so perpendicular intersections like balconies, if that intersection slab area was greater than 2% of the above ground envelope area. This translates to like if you have like balconies all along like each floor of the building, yes, you have to account for them. But most buildings, we could ignore balconies in NECB 2015. In the 2017 code, all intersections, all the balconies must be accounted for in the value calculations, as well as they added the requirement to account for all junctions in the envelope, which includes like junctions to glazing assemblies or spandrels, corners, etc. So it is a little bit different, and what this means is that when we include these items, the effective U value for assemblies generally goes down, which we will see. So methods to calculate these. If we have walls that are like a basic wood or steel framed wall and there's no major penetrations, even in NECB 2017, we can use the general calculation methods. For like wood framed, we use a one-dimensional heat flow method known as parallel path. Steel, we use a 2D heat flow method. Both of these are equation based, and so they can be completed in Excel or your software, calculation software of choice. If we have balconies or other types of intersections, then we consult the thermal bridging guide, which is a BC Hydro document created by Morrison Hirschfield. Has all kinds of different assemblies in there. It provides the effective U values, accounting for intersections, framing, all of the things. I will show a few examples from that guide, and it's a great resource for checking compliance. But first, I did want to go over those calculation methods briefly, and where this is an engineering presentation, it's always nice to have some equations in there. So wood framed assemblies to start, to calculate our effective R value. We just have two kind of basic terms. Essentially, we add up all the R values for the continuous layers, which is something like, your sheathing, your drywall, maybe there's some rigid foam or something. Add up all the R values for the continuous layers. The next term is the parallel path term. This is where you have a stud layer with cavity insulation, and those percentages in that formula can come from the National Building Code. And the percentages include like some generic estimates around like extra framing underneath windows or corners, headers, etc. So you plug all those numbers in there, get the RSI effective, and then get the USI effective as the reciprocal. So great. The steel framed assemblies equation is similar, and I won't go into those in super detail, but in general, we have these two terms. The first term is kind of the minimum thermal bridging effect term, and then the second one is the maximum thermal bridging effect term. And then there's these two constants, K1 and K2, where the value of the constant depends on the spacing, or whether there's insulating sheathing. So even if we have a steel framed assembly, kind of what this means is that we can mitigate the amount of thermal bridging or the amount of like loss in the R value by increasing the spacing if we can, or adding insulating sheathing to bring down the value of K2, so reduce that maximum thermal bridging effect term. So those are your equations for the basic walls without intersections. If we took our steel wall and we add a balcony, this is an image from the, sorry, gotta go back to where that was. Okay. This is from the Morrison Hirschfield thermal bridging guide. So you'll see within this wall, we've got exterior insulated steel stud wall assembly. It's got an intermediate floor intersection, uninsulated floor. The R value of the exterior insulation starts at R15. So already this would not be compliant in our zone because our zone is R23, but let's just start with this R15 number. If we were to apply that steel framing equation that I just showed, we would get to this R11 number. So that's the effective R value accounting for the framing in the wall. But then when we account for the thermal bridging of that slab itself, we go all the way down to R6.8, so R7, which is your 55% decrease in effective R from your starting point of that exterior insulation R value. So that's a pretty big decrease. So this is why, and even just between R11 and R7, right? So R11 would have been the value we used in the NECB 2015 code, and then 2017 code, we'd be using R7 because we have to account for that balcony slab thermal bridging. So as you can see, there's a pretty big decrease in our envelope U value. And there's my source there, thermal bridging guide. Okay, I wanted to talk a little bit about curtain walls because similar issue. Curtain walls are, if you're not familiar with that term, it's just a term for the type of wall where it's kind of sits on the outside of the building. It's very like flush and looks very nice. Lots of glass and metal. Very nice, but not typically very high performing in terms of insulation. And in curtain walls, especially if we have any kind of floor slab, so not even necessarily balconies, but if there's a floor slab that kind of intersects with the wall, that plus the studs or the framing of the wall can really reduce the effective R value. So for example, if we look at, this is our what the wall is composed of in terms of what's in there. We've got, hopefully you guys can see that, but in general, this is a floor slab coming into a spandrel panel. So the opaque part is the spandrel panel. Above and below it would be like your vision glass. So we don't need to account for vision glass in the opaque envelope. That's fenestration. That's, we'll get to that. But we're just paying attention to that opaque part, which is the spandrel panel. And in this case, that is where the insulation sits, is the back pan in the spandrel panel has some insulation in it. And then the rest of it is just, they've got drywall on the inside, etc. So when we look at the results for this wall, if we start at an R value of 16.8 for that spandrel panel section, it goes all the way down to about R5. So, and again, that's because of all of that framing around the spandrel plus that floor intersection. Okay, so it's like a 71% decrease from your back pan insulation at R16 to your opaque assembly effective insulation. So the number that you're using to check your compliance with the code is the R4.8. So R4.8 compared to the requirement for R23, right? So that definitely fails. I mean, R16 fails too, but you can see the pattern there, right? And because of this, it's really important to do these calculations. And like I've said here, effective thermal resistance calculations are an effective tool. I was trying to be funny to optimize envelope performance. So yeah, we can definitely use this in design to identify, okay, what can we do to this wall to improve its performance? But also these calculations are so important to make sure that we're complying with the code, right? Because we might think that a building is compliant if we haven't done the calculations and then go through the calculations or check the thermal bridging guide. It may turn out that the wall is not compliant, which means perhaps that the building needs to go performance path to demonstrate compliance through whole building performance. Okay. Oh, airtightness. This one's easy. Not in scope. So airtightness is there's no requirements in the NECB for airtightness. The NECB does not tell us why it was excluded, but some possible reasons. First, airtightness testing can be challenging in large buildings. It's certainly not as simple as a house, right? In a house, you can just set up a blower door, do the test, be done in like 15 minutes. In large buildings, it is certainly more complicated than that. There are some concerns around labor market availability for both the construction techniques and testing. And I didn't put on the list, but the concern too that a building, like by the time it's tested, if it really fails the test, it's kind of too late, right? Like, what are they going to do? So that was brought up as a concern, though BC has airtightness requirements and they seem to be working just fine. The third one is that NECB is an energy efficiency code and not an energy conservation code. So what I mean by that is that the NECB looks at, the total energy performance of a building, regardless of kind of what its energy demand is. So BC and Toronto, in their codes, there are thermal demand targets. So the building's, say, heating load has to be below a certain number to meet those targets. The NECB doesn't have any of that, right? And airtightness is a way to reduce heating load. So airtightness is not covered. It doesn't really matter what the leakage is, as long as the building overall meets the efficiency requirements. There are some airtightness, I guess, parameters that go into modeling, and we'll talk about that a little bit later. But in general, we don't include airtightness in the compliance. Fenestration. This one is pretty straightforward, more straightforward than the Wals. So the requirement in Zone 6, maximum fenestration and doors to walls ratio, FDWR, is 0.4. So the envelope can only be 40% windows, basically. If the proposed building has more than 40% windows, it has to use the trade-off or the performance path, right? So if you have, again, that all glass building, that has to be modeled. Requirements for windows. Windows did get more stringent. The requirement got more stringent in NECB 2017. So we went from a USI of 2.2 to a USI of 1.1, which is still very much like achievable in the prescriptive path, though there are lots of windows that don't meet that requirement. And so if they don't, then again, looking at trade-off or performance path. The NECB does not include a requirement for solar heat gain coefficient, so it would just be whatever the proposed building uses is fine. And doors don't need to comply with these requirements if the total area of the doors is less than 2%. They like the 2% number. It shows up a lot. But if less than 2% of the gross wall area, the reason for that, like if you think about it, say a building has like 2 doors that don't meet this USI requirement, like it doesn't have to be modeled just because there's 2 doors that don't meet that, right? So I think it makes sense. So that's fenestration. Okay, prescriptive HVAC. Briefly, the code has specific requirements for different system capacities and components. So depending on, say, like the size of your heat pump, there are certain performance requirements. There are minimal changes to this section between the two versions of the code. And there's lots in there, like tables and tables of information. So I won't try and summarize it, but it is there. It's fairly straightforward, easy to follow. Like I said, minimal changes, except one rather important change that I did want to go over, and that is in energy recovery systems. So in NECB 2015, we had the requirement that a system, exhaust air system, had to be equipped with heat recovery when the sensible heat content of exhaust was greater than 150 kilowatts. The sensible heat content of exhaust is determined from the flow rate and design temperatures. There's an equation in there. Generally, this, it would apply to fairly large systems, so bigger buildings. Whereas in the 2017 code, we have the requirement that all continuously operating supply air systems must have energy recovery. So we essentially went from most buildings didn't need it to now pretty much every building needs it, except for if there's a system that serves a single dwelling unit for zones 4 to 6, so including our zone, those systems do not require energy recovery. But everybody else, so office buildings and retail, etc., they all have to have energy recovery with minimum effectiveness of 50%. If there's no energy recovery in the proposed building, then you're looking at trying to comply via performance path and balance that off with something else, right? Maybe better envelope. And yeah, this is a big deal. This changes the efficiency standard for those buildings like quite a lot, because there's a lot of heating load in that extra ventilation, right? So that was a big change in NECB 2017. Okay, we've got to the Part 8 section. So Part 8 is the Building Energy Performance Compliance Path. So within this section, there's everything you need to know about using performance path, and I'm just going to try and summarize a bit of it because there is lots there. And this is what the NECB says about that section. So compliance is permitted to be achieved by applying this part in lieu of prescriptive or trade-off, right? So you choose performance path if you're not going to choose those other paths. So if you're already good under prescriptive and trade-off, then you don't have to worry about performance path. Many buildings are choosing performance path just because of the flexibility, it seems. Okay, general requirements. So you do have to have complete design information. So like, the design has to be done, but also, we have to have occupancy information as well as selection of like materials and assemblies. The energy model that's being used has to calculate at maximum 1 hour intervals for a full calendar year. So that's an 8760 hour model. The total energy in the proposed building must be lower than the reference building. Yep, that's how it works. And generally, there's a little change in Part 8 with the NECB 2017 revision. There's a couple small notes that were added, but generally the requirements are the same. Okay, common software options for achieving compliance, eQuest or CanQuest. CanQuest did have an auto-generated compliance model for NECB 2011, but that has not been updated, so it's not really valid anymore. There's the hourly analysis program, which is HAP by Carrier. It doesn't have any NECB content. Then there's IES virtual environment. They did recently announce a compliance tool for NECB 2017. I haven't used it, but it's there. It seems like it's a big deal. And those are just a few. There's other softwares that are available. All of them have their own pros and cons, but they all work. They're all great. That could be a whole other session just talking about the softwares, but certainly, yeah, they all do work. As far as including systems in the models, the energy model, and this is requirements from the NECB. So within the model, we have to have space heating equipment, shocking, cooling, lighting, surface water heating, so that's your domestic hot water, your pumps, auxiliary HVAC, which is like humidifiers, receptacle loads, and miscellaneous equipment. I have a star there because there aren't performance requirements for those, but they're included in the model for the interactive effects, and elevators and escalators. Things that are excluded from the model, backup HVAC. Yep, because if it's not going to run, then we're not going to model it. That's it. All the other stuff has to be included. So defining the reference building. So you've got your proposed. The proposed has all of its design information, all good. You can make that model. Defining the reference building is where you're checking back to the NECB to see, okay, what does it tell you that has to go into this building? So I'm going to go over again some of the requirements because there are lots, and also best practices because there are a few gaps or contradictions, ambiguities, so we kind of have to rely on some best practices to fill those gaps. In general best practices, do follow the NECB requirements as outlined. So if there's a requirement there, try and follow it. If there's not a requirement, try and use good engineering judgment about what's reasonable for a reference building. And then also do critically assess model results. So we want to make sure that we're looking at all the results of both the reference and the proposed model to make sure that it's reasonable given the building design, right? So maybe looking at the energy use intensity and thinking about whether that's reasonable for the type of building, etc. Don't expect to find all the answers in the NECB. Yep, there's lots in there. It's a great code, very comprehensive, 340 pages, but there's certainly some things that maybe are just not there. Don't expect the NRC to provide interpretation guidance. They will send you a very lovely, polite letter, but they probably won't guide you in interpretations. And also don't expect the NECB to be like ASHRAE 90.1. ASHRAE is a lovely code, lots of great stuff in there. We don't use it in Nova Scotia, so we can't rely on it for compliance calculations. And also in general, do ask colleagues and industry for help. There are lots of people that use the NECB. There are lots of people that find the NECB somewhat challenging at times. So yeah, it's always good to ask others what they're doing. Feel free to ask me. My contact info is going to be at the end here, but yeah, always happy to chat about it. Okay, the reference building. Yeah, we've got a whole section on it, 8.4.4. In general, the components within the reference building are meant to follow the prescriptive path, like I said earlier. There are some characteristics of the reference that have to be identical to the proposed. This includes the total floor area, makes sense. Occupancy and schedules also makes sense. Number and type of thermal blocks, where the thermal block is one or more zones that are served by an HVAC system. This one I'm going to put a little star by it because we're going to come back to that later. So it's supposed to be identical, right? Shape and dimensions have to be identical, as well as orientation. So these last two here, what this means is that there's no credit given for improved massing or orientation. We know that those are important things when we're designing efficient buildings, but when those design decisions are made, that doesn't necessarily give you credit within the NECB. All right, so looking at envelope, pretty straightforward. U values follow the prescriptive requirements. And remember to calculate that effective U value for the proposed, right? So the reference, they are what they are. It's R20, R23, right? But for the proposed, we always have to make sure that we're doing those calculations. Window to wall ratio. If the proposed window wall ratio is greater than 0.4, then the reference is equal to 0.4, again, for zone 6, because this is a zone-dependent number. If we've got a proposed building where there's less than 40% windows, the reference is identical to the proposed. Airtightness. So we talked about airtightness, how it's not in scope, but we do have to put something in the model, right? Because it's there. Air leakage affects the building's energy use. So the NECB tells us that the reference and the proposed are each modeled at 0.25 liters per second per meter squared of envelope area. This number here is not a prescriptive criteria, right? So this is for calculation purposes only, and the NECB actually says that because this would be a fairly stringent requirement. Like a lot of buildings would not be able to meet that value. So it's just for modeling. It's not any kind of actual criteria, but that's what we're supposed to put in there, okay? HVAC. Okay, I said that needs its own section, easily its own lunch and learn. I could talk about this for a long time, but I'm going to try and be brief. And if there's questions, hopefully ask them afterwards. There's a table in NECB 8.4.4.7, which helps us select the HVAC system in the reference, and it's based on the type of the proposed building. So here's the table. If anyone's on a small screen, you can probably barely see that, but it's all kinds of different building types, and then based on the building type, it'll tell you a system number, and then it defines the system numbers. So if we look at two kind of common building types, general area, which is like lots of different buildings, offices, healthcare clinic, library, gym, etc. Those are general area. And then we also can look at residential or accommodation area. So this would be like your multi-unit residential buildings, of which there are lots going up in Halifax. So for our general area building, if we follow the table, the HVAC system selection would go like, if the building is less than or equal to 2 stories, we have system 3.
Yeah, Anne, you're coming in and out.
If it is greater than 2 stories, system 6. People are saying that the sound is getting lost.
A bit, so I don't know
I'm
if
just gonna
there's
take a
a
little break to
connection
make sure
issue.
lots of people are finding sound. Hello?
We can hear you now, so we'll see how that goes.
Let me just try. Let's try that instead. Is that better? Okay, I just like changed. I had a headset, so I changed it to laptop. So, okay. Hopefully people didn't miss too much, or hopefully
It's
as I was
choppy,
speaking, you
so I
could
don't
follow along
know.
with what's on the slides.
Is there
If
anything
there was
else we can
something that
try here?
didn't
Is
come
there
out and you had
any?
questions about it, just
Yeah, we're still getting
just let me know at the end. Okay.
Okay.
So
the platform. Anthony is saying. And could we get you to try leaving the room and coming back in?
okay. Hi. Yeah.
Not really sure what else
Can
to
you hear me better
try.
now? Yeah. Yeah, it's really choppy here. Like I can barely hear you.
It's still a little choppy. So
is it okay now?
yeah, the only thing I can think of is maybe to try to have you leave the room and come back into the meeting. Oh, okay. I think the sound is good right now. We'll just see how it goes.
Okay, how do I do that?
Sorry, Anne. Yeah, it sounds okay now.
Yeah, sorry about that. I don't know what's going on. It seems fine here. It sounds okay now though? Weird. All right. Okay, I will try it and keep going. I hope it's I hope it's all right. Okay. So, I'll jump back into where I was. Folks, just let me know, like in the chat there on the side, if it's, if it gets really bad again. Thank you, Sean. Okay, so table 8.4.47, HVAC system selection. Okay, general area. So that's, as I was saying, that's like our office type buildings, healthcare clinics, libraries, etc. Those buildings, if it's less than or equal to 2 stories, we have system 3. If it's greater than 2 stories, system 6, and I will show what those are. If we have a residential accommodation area, it's a little bit more complicated. So if there's no cooling in the proposed, we choose system 1. If the proposed has both heating and cooling, and if it has fan coils, terminal air conditioner, or heat pumps, or then the reference building's HVAC is identical to proposed. If it doesn't have fan coils or terminal AC, then the NECB tells us to use through the wall systems, which we interpret to be a PTAC. So those actual systems, we've got another table that shows us what they are. So system 1 is unitary air conditioner with baseboard heating, so also pretty much a PTAC, package terminal air conditioner. System 3 is single zone packaged rooftop unit with baseboard heating. System 6 is a multi-zone built-up system. So this is the only one that's a multi-zone. The rest of them are all single zones. So those are your system types, okay? And then the type of heating system in those systems has to match the proposed. So if the proposed building has fuel-fired heating, then the reference is going to have a fuel-fired boiler plant. If the proposed has electric heating, then the reference is going to have electric resistance baseboards or electric furnace heating coil right in the rooftop. Okay. As far as ventilation in your reference HVAC systems, systems 1, 2, 5, and 7, those ones NECB tells us to that the building has to have one ventilation system. So you've got all these single zone systems, and when we use those systems, the building is supposed to have a single ventilation system, except for dwelling units. For buildings with dwelling units, the ventilation system must be identical to proposed. For the other systems, so 3, 4, and 6, the NECB does not tell us. So it just doesn't say anything. So in this case, we enter our best practices, such as identical to proposed, or maybe there's packaged HVAC as appropriate, right? So use your good judgment. And also don't forget about energy recovery in the reference. So these are our reference systems. So our reference ventilation system must have energy recovery if we're working with NECB 2017, which we probably are for many buildings, right now in 2020 or 2021. Okay. Oh yeah, and a little note here, ventilation air rates for both the reference and the proposed are per the applicable ventilation code, which per the National Building Code is ASHRAE 62.1 for most buildings. So we use those rates regardless of the design CFM. So even if a building is designed to be like over ventilated for whatever reason, we use the ASHRAE ventilation rates in the models for compliance purposes. Okay. Zoning. Okay. So the systems that you'll select for the building, all the single zone systems, 1 to 5 and 7, their zoning should match the thermal block zoning and proposed. So even though the NECB tells us that it's a single zone system, we have to keep in mind that at the beginning, the NECB told us that the number and type of thermal blocks in the reference has to match the proposed. So for example, say we have a general area type building and it has 2 rooftop units and they each serve 5 zones. So based on this, right, so then we've got like 10 zones total. So based on this, the reference building could have either 10 single zone rooftops because it's a single zone system, or 2 single zone rooftops where each of these are actually serving a single thermal block, but the block has 5 zones in it. So the correct approach would be to use the 2 single zone rooftops, because it's more representative of the proposed design, but also, yeah, that's the one that is making sure that we have the same number of thermal blocks, right? So yeah, just something to keep in mind, like that matching the zoning is really important for the reference model. Fan power, also a great topic. Part 8 does give us requirements for fan efficiency in the reference systems. So all of the single zone systems, 1 to 5 and 7, they all have the same requirement, which is 640 pascals of static pressure and 40% combined efficiency. And this works out to about 0.75 watts per CFM. All of those systems are constant volume in the reference, regardless of what's going on in the proposed, right? This value did not change from NECB 2015 to 2017, even though we now need to have energy recovery on those systems. What this means is that if we have a proposed building that has a high efficiency ERV, we might see that the proposed fan power is actually higher than the reference. So there's going to be a penalty on that fan power because of the pressure drop across the high efficiency ERVs, right? So I'm not sure why they didn't update it. Again, they don't necessarily tell us. Hopefully that's something that's going to be addressed for the next revision, because we do want buildings to choose high efficiency ERVs, but we don't want to see penalties on fan power, right? Okay. Fan operation in general. So this is how your fan should be operating in the model, both models. If the fan is only providing heating and cooling, then it operates on the call for heat and cool. Great. If the fan is providing fresh air, it operates whenever the space is occupied, right? Because the occupants always need fresh air. And this applies to the reference and the proposed, and the fan operation should match. So if you have a rooftop that supplies fresh air in the proposed, it supplies fresh air in the baseline, which can sometimes contradict what the NECB says. But again, we should have those systems matched. Okay, let's do, now that we have all that information, I want to go through an example system selection for our HVAC system. So this is our building. So we have a proposed 2-story office building. It includes a packaged rooftop serving mixed air, so the fresh air is in there. And this rooftop is serving 2 meeting rooms and 4 offices. The rooftop has a gas furnace and DX cooling, and the proposed rooftop does not have exhaust air energy recovery, unfortunately. That happens, right? In the zones, we have hydronic baseboards in the meeting rooms, but not in the offices. So the reference system for this building would be a single package rooftop, system 3, with a gas furnace and DX cooling, because again, we want to match that fuel type. The meeting rooms in the reference would also have hydronic baseboards to match the proposed. The rooftop fan is running at constant speed whenever the building is occupied because it's supplying fresh air. And the fan would also have that 640 pascals, 40% efficiency number. The system would be equipped with exhaust air energy recovery in the reference, right? So you might have a bit of a penalty there for the proposed. The reference boiler plant would be modeled with the NECB performance standards for the boiler plant, right? For those hydronic baseboards. So that would be your reference system. Awesome. It's pretty straightforward. Unless you have a heat pump in a thermal block, in that case, start again. And it's not exactly a start again and being dramatic. For each thermal block of the proposed building, have an HVAC system that includes a heat pump. This is from the NECB. So essentially what this is saying is that, yeah, if you have any thermal block that has a heat pump, the reference has to have a heat pump, or specifically, as they say, go over to this new section. So forget about that table, go to this new section, section 13, which talks about heat pumps. And so if the proposed has an air or water or ground source heat pump, then essentially what happens is that your reference is also a heat pump. So all of those reference systems I described don't necessarily apply if you have heat pumps in the proposed. So the reference system for heat pumps is an air source packaged unitary rooftop heat pump with auxiliary or supplemental baseboards, where the star is that except for system 7, which serves ice rinks, you don't need a reference heat pump. I mean, ice rinks, they're their own thing, so it's very rare, right? The baseboard fuel type is to match the proposed, just like the other systems. So that's for all of those types of heat pumps. But if your proposed has water loop heat pumps, then you go back to the table. So it just sent you in a loop, in a circle. But the rest of them, so if we have a building with, say, mini splits or a heat pump in the rooftop unit, then the reference has to have a heat pump. Okay, so defining the reference heat pump, so what actually goes in there. NECB provides some rules around capacity, so it's size for the zone's peak cooling load, and then the heating capacity at 8.3 outside air is equal to the cooling capacity. The heating in those units is available down to -10, so if your building is using heat pumps that perform to colder temperatures, then you're going to get credit, right? Performance of the reference heat pump, the NECB has part load performance curves as well as the prescriptive requirements for heat pumps that reference one has to follow. Fan power for your reference heat pump, yeah, we don't know, or it doesn't tell us, right? Ventilation system for the reference heat pump also doesn't tell us. So again, enter our best practices. And so for fan power, we would assume that this packaged unitary rooftop heat pump system is similar to system 3 that we talked about earlier, in which case we would apply that 640 pascals 40%. And the ventilation system, we would assume that we're going to use identical to proposed, which could either be a dedicated outside air or integral to the heat pump if it's part of a rooftop, etc. But if we choose identical to proposed, then at least we're being consistent, right? Okay, everything else that I didn't cover refer to the code. You can get your free PDF from Codes Canada after going through their slightly onerous process. I would highly recommend, to avoid eye strain, use bookmarks, which are like embedded into it, as well as your Control F. And that is the end. There's the references that I consulted in this presentation. There's my email address if you want to contact me about modeling or the program. And I would be happy to answer some questions if people want to put them in the chat, or I don't know, Beth, if people can use their mics for questions, but I will certainly monitor the chat for questions. Yeah, thank you. Steve asked, how are municipal authorities educated on requirements? The municipal authorities, I mean, they would have their own processes internally for, like training on requirements. But again, that's fairly inconsistent. So it's kind of incumbent on the municipality to, have their employees trained. And so that does mean that some municipalities, even within Nova Scotia, maybe there are some that are better than others in terms of knowledge around code requirements and how to enforce those requirements. So that's one that's, and it's a little tricky to assess. Like, we haven't necessarily done work in Nova Scotia to be able to say how much the municipalities do know, but in general, across all kinds of different jurisdictions, Canada and US, there is sometimes a knowledge gap at the municipal level with energy codes. Can you combine prescriptive and performance compliant pathways, and have you noticed recurring non-compliance issues? I mean, I can't really speak to the non-compliance issues, like, because I don't work for the permit office. But to the first part of the question, can you combine the pathways? I mean, as soon as you're starting down the performance path, then you're committed to performance path. And so, you would use prescriptive path if you can. If you're able to meet all those requirements, then you use that path. Performance path, when you have any system that requires you to go down performance path, you have to do that for the whole building, because it's a whole building compliance. Yeah, sure, Tony, just send me an email and I can send you the slides. I'm going to see if there's any other questions, but I think if there aren't anything right away, then I'll sign off. I hope that people were able to hear most of the presentation. I'm sorry about the audio issues. Not sure what's going on there. And if you do still have follow-up questions, again, please feel free to contact me, my email. Thank you, Corey, for confirming that. It makes me feel a lot better.